Okay, thank you, Jan, for the presentation. My name is Luca Corsaro from Politecnico di Torino, and I concluded my PhD in July, and this presentation entitled Passive and Active Thermography for Surface Treatment Characterization in Spur Gears was part of my PhD thesis. In this work, there is a wide application of thermography for the surface treatment characterization in case of gears. Thermography in active configuration was adopted for the characterization of residual stresses produced by the surface treatment, and thermography in passive configuration was adopted for the fatigue limit estimation by using the well-known thermographic approach in case of a mechanical component as gear. Now I will show you how active thermography can be utilized in the topic of the surface treatment characterization. The goals of this activity consisted in the development of a non-destructive thermographic procedure for the characterization of gears after the surface treatment and the characterization of residual stresses by using an alternative approach in terms of active thermography. There are several case studies, such as different materials, different gear geometries, and different surface treatments. Just a brief description of active thermography technique. The main difference with respect to the classical passive thermography is that the component increases its temperature thanks to an external heating source. And there are several heating sources for this purpose, such as flash lamps, induction heating, and laser. And the heating phase can be realized with two approaches that can be explained with the classical mechanical vibration theory. The first approach is called a pulsed technique, and it generates an impulsive heating over the surface of the sample, and the consequence is a free thermal response. The second approach is called lock-in technique, and it produces multiple heating over the surface of the sample, and the consequence is a forced thermal response. Then the equipment can be adjusted in order to obtain two different experimental setups. One is called reflection mode, and in this case, the thermal camera and the excitation source are located in front of the sample. And the second experimental setup is called transmission mode, in which the equipments are located at the opposite side. The starting point of this activity was this question. So, can active thermography be an alternative, non-destructive technique to characterize surface treatment? The effects of the surface treatment in terms of mechanical properties are well known. In fact, the microstructural alteration is responsible for residual stresses increments and hardness increments. But what is the effect of the microstructural alteration in terms of thermal property? So to answer this question, a dedicated surface treatment investigation on cylindrical samples was previously performed by using classical equipment, and mechanical properties were investigated with classical hardness meter and X-ray diffraction meter, while thermal property as thermal conductivity was investigated with the classical hot disk, and both treated and untreated materials were investigated. Here I tried to summarize the results obtained from this surface treatment investigation, and on the left side I reported the results in case of induction hardening surface treatment for a C45 steel, and on the right side I reported the results for a carburizing surface treatment in case of a 20 manganese chromium 5 steel. Moreover, the red colors are referred to the untreated or base material properties, and the green colors are referred to the treated material properties. And as you can see, focusing the attention on the mechanical properties, the microstructural alteration produces an increment in both hardness and compressive residual stresses for both the surface treatment as expected. But there was also an unexpected result regarding the thermal properties. In fact, there is a thermal conductivity reduction for the treated material. So at the end, a global anti-correlation phenomenon was obtained between the mechanical and the thermal properties. So at the end, this microstructural alteration affects both mechanical and thermal aspects, and the potentialities of active thermography can be adopted to investigate this microstructural alteration. Regarding the method, a preliminary feasibility analysis of active thermography was performed on the cylindrical samples, but today I will show you only results regarding gears. And in our laboratory, there is a laser as heating source, and it is controlled by acting on three factors: the power, the step duration, and the number of cycles in order to realize multiple heatings and to reproduce a lock-in technique. A design of experiment approach was adopted for the tuning of these laser parameters, and at the end, the active thermography method was defined as follows. The base material or the untreated material was chosen as reference material since it has a very low value of residual stresses, but it is also easy to characterize thermally, as an example, by using hot disk. Then a thermal index was necessary to perform the surface treatment characterization, and the most useful thermal index from active thermography point of view is the thermal diffusivity, since it is very easy to estimate by using active thermography. Then the laser parameters were properly optimized with the design of experiment approach in order to try to reproduce a base material thermal response in terms of thermal diffusivity. This way, different thermal responses means microstructural alteration and the presence of the surface treatment. So basically, the procedure is composed by 4 parts: the experimental test, the data elaboration, the thermal index evaluation, and then the comparison between the mechanical and the thermal properties. Regarding the target response in the design of experiment analysis, the base material thermal diffusivity evaluated with the hot disk was chosen for the tuning of the laser parameters. Regarding the active thermography thermal index, the thermal diffusivity was evaluated by using the slope method that is realized with a lock-in technique in reflection configuration. And then the active thermography analysis was performed with localized heating over the tip of the tooth, and then the thermal responses were extracted from the tip of the tested tooth. In this picture, I reported in this slide, I reported 2 different pictures regarding the gear geometry. In particular, 3 mm and 4 mm moduli were utilized in this activity, and for each gear geometries, 3 different surface treatments were investigated: the induction hardening and the carburizing with the shot peening surface treatment. In this slide, there is an example of the active thermography setup in the reflection configuration. There are the laser, the thermal camera, and the FPTA lens that was very useful to locate the laser over the tip of the tooth. But there is also this device named gear holder that was manufactured with 3D printing that was very useful to fix the gear always at the same position during the active thermography test. In this slide, I reported the active thermography results for the induction hardening surface treatment. In particular, on the left side, there are phase maps, and basically the phase map is one of the possible lock-in results, and it corresponds to a thermal delay as a phase signal in the mechanical vibration. And on the right side, I reported the phase profiles extracted from the tip of the tested tooth for both the gear geometries, so the 3 mm modulus and the 4 mm modulus. And the red colors are referred to the untreated gears, while the green colors are referred to the induction hardened gear. And as you can see, there is a thermal response alteration in the heat propagation zone. So this means that the microstructural alteration as a result of the induction hardening surface treatment can be detected with active thermography. Similar consideration can be drawn also for the carburizing and the shot peening surface treatment. In fact, there are thermal responses alteration in the heat propagation zones. So this means that also the microstructural alteration caused by carburizing with the shot pinning surface treatment can be detected with active thermography. So once the phase profiles were extracted, the thermal index can be evaluated by using the slope method. In fact, the slope of the heat propagation zone is related to the thermal diffusivity thanks to this formula. And now in this slide, I reported the surface treatment characterization performed by using active thermography in case of induction hardening surface treatment. So there is a comparison between the thermal index and the corresponding mechanical properties of the tested gears. It's important to note that in this case, the thermal index corresponds to the thermal diffusivity evaluated with active thermography by using the slope method. And focusing the attention on this graph, the gray bars are referred to the thermal index, while the black lines are referred to the mechanical properties. And moreover, I reported on the left side the results regarding the 3 mm modulus gears, and on the right side, the results regarding the 4 mm modulus gears. And as you can see, there is a thermal diffusivity reduction detected by using active thermography as a consequence of the microstructural alteration produced by the surface treatment. But this microstructural alteration is also responsible for the hardness increment and the compressive residual stresses increment. So at the end, also by using active thermography, a global anti-correlation phenomenon between thermal and mechanical properties can be detected. Similar results were also obtained in case of carburizing and shot pinning surface treatment. In fact, a global anti-correlation phenomenon was also obtained between the thermal diffusivity and the mechanical properties in terms of hardness and compressive residual stresses for both the gears geometry. So at the end, the lock-in technique was identified as the optimal active thermography technique for the surface treatment characterization. The design of experiment approach provided an optimal laser parameters combination for the two investigated surface treatments, and a standardized experimental setup was also defined. Then the two different moduli did not alter in a significant way the results. So at the end, the thermal responses can be considered as localized measurements. Then a global anti-correlation phenomenon was also obtained in case of gears and by using active thermography. And these results were previously confirmed with the surface treatment characterization realized by using the classical hot disk equipment in case of cylindrical samples. Now I will show you the passive thermography activity, in which the goals consisted in the investigation of the feasibility of the thermographic approach for a reasonable fatigue limit estimation in case of gears, and the development of an equipment for bending fatigue test on gears by using a mechanical pulsator. It's important to note that the thermographic approach is a well-consolidated methodology in literature for the fatigue limit estimation, but in case of classical cylindrical or flat specimens. Just a brief introduction about the thermographic approach. In this work, the true curves method was utilized for the fatigue limit estimation, and the fatigue limit is estimated by means of thermal emissions during the fatigue test, thanks to thermal parameters such as the thermal increment or the thermal area that are properly evaluated from thermal responses acquired from by using a thermal camera. Then the fatigue limit is estimated from the intersection of two curves that and these two curves approximates the thermal parameters evolution obtained for different stress levels. Then, if linear approximating curves are adopted, the method is called original TCM. While in case of parabola power law approximating curves, the method is called modified TCM. In this slide, I reported the equipment for the single-tooth bending fatigue test on gears with a mechanical pulsator. The equipment is composed by two handles, and the load is applied to the gear near the high point of the single-tooth contact. In this slide, there is a description of the passive thermography activity. In particular, two 3mm modulus gears were tested, one made of C45 steel without the surface treatment, and one subjected to the induction hardening surface treatment. In this scheme, I try to summarize how the two curves method was adapted in case of gears. And regarding the stress level, so the x-axis, the stress level for sample is referred to the amplitude stress, while in case of gears, the two-fruit stress calculated according to the ISO standard was considered. Regarding the thermal parameters, thermal increments or thermal area were also considered for gears. Regarding the two curves method results, the intersection of the approximating curves defines the fatigue limit, and in case of samples, the intersection corresponds to the fatigue limit related to the testing conditions, while in case of gears, the intersection was referred to the permissible bending fatigue stress of the gear. In this preliminary work, reference values of permissible bending fatigue stresses were evaluated by using ISO standards computation, and then these results were compared with those obtained from the two curves method routine. In this table, there is a description of the experimental campaign data for the two tested gears. In particular, there are the testing frequency, the load, the two-fruit stress, and on the right side, I reported an example of the thermogram obtained during the fatigue test and the corresponding experimental setup at the mechanical pulsator. In this activity, the thermal responses were extracted from the two-fruit of both the tested teeth. In this slide, there are the thermal responses obtained from the untreated gear, and as you can see, a stabilization temperature trend is not reached, and the two teeth show different thermal emissions for high stress values. Regarding the thermal parameters depicted in this two graph, two different linear trends were obtained for the thermal increment and the thermal area. Here I reported the results obtained from the two curves method routine. The thermal area was preferred as a thermal parameter since low temperature increments were generated during the fatigue test. And in this case, the linear approximating curves allowed the optimal thermal parameter approximation below and above the fatigue limit. So at the end, the permissible bending fatigue stress estimated with the two curves method was in good agreement with the reference value obtained from ISO standard. Similar considerations can be drawn also in case of the treated gear. Also in this case, a stabilization temperature trend is not reached, and the two teeth show different thermal emissions for high stress values. In this case, the thermal parameters reached higher values than those obtained in case of untreated gears. And regarding the thermal parameters, an abrupt thermal emission was detected for high stress values, and no thermal parameters increment were detected at low stress levels. In fact, there is a flat behavior. Here I reported again the results obtained from the two curves method routine. Also in this case, the thermal area was preferred as a thermal parameter, and in this case, the linear approximating curves and the parabola power law approximating curves provided similar results in terms of permissible bending fatigue stresses. But in this case, the estimated values were lower than the reference value evaluated from ISO standard. And the reason is due to the fact that the induction hardening surface treatment realized for this gear is not properly optimized for a bending resistance, while the reference value considers a tooth root optimized for a bending resistance by the surface treatment. So at the end, the feasibility of the thermographic approach in case of a complex mechanical component such as gear was investigated in this activity, and an equipment for the bending fatigue test on gear was properly designed to perform tests at the mechanical pulsator. In case of gears, the thermal area was the most suitable thermal parameter, since slow temperature increments were generated during the fatigue test. And in this preliminary study, reference values were calculated from ISO standards computation. And for what concerns the untreated gear, the permissible bending stress estimated with the two curves method was in good agreement with the calculation obtained from ISO standard. On the other hand, the treated gear showed a lower permissible bending fatigue limits if compared to that calculated from ISO standard. And the reason is due to the fact that the surface treatment is not properly optimized for a bending resistance. But in any case, an increment with respect to the permissible bending fatigue stress obtained from the untreated gear was obtained as a consequence of the overall induction hardening surface treatment. For the future, validation of the proposed method will be carried out by considering reference values obtained directly from staircase method on gears. So, general conclusions of this activity. Regarding the active thermography activity, the aim was to explore the potentialities for the characterization of different surface treatment realized on Spur gears, and an alternative non-destructive setup based on active thermography was developed and was well validated in case of induction hardening and case hardening with shock peening surface treatments. Regarding the passive thermography activity, the aim was to investigate the feasibility of the thermographic approach for a reasonable estimation of the fatigue limit in case of Spur gears, and the two curves method confirms its potentialities for a rapid fatigue limit estimation with respect to the classical staircase method. And in case of gears, a preliminary validation of this approach was obtained with reference values calculated from ISO standard, but a more reliable comparison will be performed with reference values evaluated from staircase method directly on gears. Thank you for your attention. My presentation is concluded.
Okay, Luca, thanks very much for your presentation. We have a couple of minutes for maybe one or two, maybe three questions.
Okay.
Is there anybody curious on the results of Luca? I was very fascinated by the research you did concerning the thermal conductivity and its dependence on previous hardening. That for QT you are getting much lower values of thermal conductivity, which is probably something what we observe as well, and maybe you will also see that during the test which you should proceed with for the Faber.
Yes.
For the specimen which I sent you.
Yeah. And
I wanted to ask one question because of apparently those different processes, shoot peening, quenching tempering, and so on, all of them proceed with some kind of microstructural alterations. So technically, when you show us those graphs with the difference in the slope of the central section, it is obvious that you see some dependency. This is here.
Okay.
Do you think is it possible to, when you get more data, to recognize what could be the reason for this alteration? Because we are looking for some industrial application of this.
The goal. Sorry. No, sorry.
Yeah, please continue.
No, the goal is to try to use active thermography as a non-destructive approach. I mean, the classical residual stresses evaluation in case of complex mechanical components such as gears involving the destruction of the component. So in this case, the idea is to avoid the destruction of the component by using thermal signals in order to detect thermal alteration and, as a consequence, microstructural alteration and the presence of the surface treatment.
Okay, thanks a lot. Please, any more questions?
Can I ask one question?
Okay.
Thank you for your presentation. I was interested by your test setup for testing gears. Did you design it for a resonant machine?
Yes.
Okay.
The idea was to use the classical European approach in which two handles are involved during the fatigue test of the teeth, and this equipment was developed for an high-frequency mechanical pulsator. In fact, the testing frequency was more or less 150 hertz.
Mm-hmm. And were you dealing with some, let's say, yeah, I see that the part of the apparatus is yeah, the back part to say is used to, let's say, capture the transversal load, if I'm not mistaken. Is it correct?
Yeah. So this part was useful for the positioning of the gear, since it's important to locate the tooth and near the handle with the so-called wild upper approach. And but this was also useful to fix the gear during the fatigue test due to the high testing frequency.
Okay, thank you.
Okay, Luca, thanks for the interesting presentation.